Cheesy squeezy, it's a breezy. Welcome back, math nerds. We're going to talk about limsups and liminfs of sequences of sets. Remember, we have these definitions for supremums and infimums of sets. We also have definitions for sequences of sets. Now we can do it in a kind of similar way, but not exactly the same as we did for sequences of numbers. Given a sequence of sets, we don't just talk about sups and infs of the sets and do the same thing. What we do is a bit different. Here we have it. Okay. The liminf is the union of a bunch of intersections, and the limsup is the intersection of a bunch of unions. Now, yes, they are, much like our other definition, limsup and liminf of sequences, similar operations in opposite order. Remember, the liminf of a sequence was the supremum of a sequence of infima, and the limsup was the infimum of a sequence of suprema. So similarly here, we've got union of intersection versus intersection of union. But what does this nasty construction really represent? Let's figure it out. So here we've got limsup and liminf, just the definitions restated. Now, let's take a look at this intersection that's part of liminf. What does it represent? It's the intersection of a sub n, where n goes from capital N to infinity. So to be in this intersection, you have to be in every single a sub n, beginning at index capital N and going on forever. But then that's a very restrictive condition, right? You have to be in every single a sub n past a certain point. But we then union over all of them. Okay, so there has to be some point past which you're in all of them. In order to be in this union over all n, we're just looking at the liminf definition right now, you have to be in one of those intersections. So there must be some capital N so that you're in every set past that point. So for x to belong to the liminf of an, it must belong to one of the n's in the union. So there must be a single capital N so that you're in that intersection from capital N off to infinity. To be in the liminf, there must be a capital N and you're in, and then x has to be in every single set past capital N. Similarly, let's look at the limsup. The union of the ANs is pretty permissive. To be in the union as n goes from capital N to infinity, you just have to be in some a sub n. But then you must be in the intersection. So for every capital N, you have to be in some set bigger than that. So the liminf are those sets which are in every single an at least past a certain point. In other words, you only fail to be infinitely many. The limsup, in contrast, have to be in some an past every point, and they have to do that infinitely many times. So the liminf are the elements of the reals which are eventually in everything. Past a certain index, they are in every single a sub n. The limsup are those numbers that are eventually in one. Past every index, there is a bigger index and you're in that set. So the liminf are those numbers that are in everything past a certain point. In other words, they are only not in finitely many of the sets, whereas the limsup is just stuff that is in the sets infinitely many times. So let's take a look at an example. A sub n is the interval from n to infinity. I claim the limsup and the liminf are both empty. The sets are unbounded. We are not talking about sups of sets or infs of sets. The limsup and liminf was a different construction. So even though the supremum of an is infinite, and the limit of that would be infinite, the limsup is not a number, it's a set. And it's the empty set in this case. So here are our sets. We have, say, 0 to infinity. Then we have 1 to infinity. Then we have 2, etc., etc., etc. Okay, 3 to infinity, 4 to infinity, 5 to infinity, and so forth. Now what happens if I were to take the union starting at capital N and going to infinity of these intervals? Well, the union would just be the first thing. So if I took the union from 2 and beyond, I'm really just going to have the interval from 2 to beyond. So this is just going to be the interval from N off to infinity. What about the intersection? Well, what happens when I intersect the interval from 2 to infinity with the interval from 3 to infinity? I just get the interval from 3 to infinity. But if I also intersected with 4 to infinity, I'd have 4 to infinity. And if I also intersected with 5 to infinity, and so forth. So what do you get if you intersect all of the intervals from n to infinity? You're going to get the empty set. There is no number that is in all of those things. So let x be an arbitrary real number. Natural numbers aren't bounded above, so x is not an upper bound of the natural numbers, which means there's a natural number bigger than x. Meaning, x is not in the interval from n to infinity. So for any n bigger than that, we're also not in the interval from n to infinity. This means x is not in any of the intervals from n to infinity past a certain point, which means it's not in that union and it's not in that intersection because it's not in any of them. So since there is some union that it's not in, it's certainly not in all of them. So it's not in the intersection of all the unions. It's not in the Limsup. But it's also not in any of the intersections. So it's not in the union of all of them. It's not in the liminf. So there is no real number in the Limsup, and there's no real number in the liminf. They both have to be empty. So here's another example. an is an interval of the following form, 0 to 2 plus negative 1 to the n. I claim the Limsup is the interval from 0 to 3, and the liminf is the interval from 0 to 1. So let's take a look at what these intervals do, okay? So we've got 0, 2, 2 plus negative 1 to the n. This is our interval a sub n. So for n equals 0, we have 0 to 3. But for n equals 1, we have 0 to 1. Then we're going to have 0 to 3. Then we're going to have 0 to 1. Then we're going to have 0 to 3, and so forth. So to construct the liminf and the Limsup, the question becomes which x are in, let's just say, the liminf of the an. This will be x's which are in all a sub n past a certain point. There must be some point past which x is in every single remaining set. But since these just go back and forth, notice if you're in between 0 and 1, you're in all of them. So you're in all of the sets past the first one. But if you're bigger than 1, there's always going to be times that you're missed. I can never say, oh, cut off the first 350 sets and past that point, 1.5 is in all of them. No. Since I go back and forth between 0301, 0301, anything bigger than 1 will be missed over and over and over again. So there is no point past which it remains in everything. So everything from 0 to 1 is in all of the sets. Anything bigger than 1 misses over and over again and therefore is not in the liminf. But what about the Limsup? The Limsup, this is an x which is in infinitely many a sub n's. Which x's are in there infinitely many times? Anything from 0 to 3 is in it here, and then here, and then here, and so forth and so forth. Okay, so we just have to formalize that idea. So if x is negative, x is not in any of them, and if x is bigger than 3, x is not in any of them, which means it's definitely not in it infinitely many times. So it's not in the Limsup and it's not in the liminf. Suppose you take something in between 0 and 1. Since it belongs to every single interval, it belongs to any intersection or union I can construct out of them, and therefore it must belong to both the Limsup and the liminf. Okay, so everything from 0 to 1, since it's in every single set, it's in the Limsup, it's also in the liminf. What about numbers in between 1 and 3? then you're in A sub n if and only if n is even. There are infinitely many evens, but there are also infinitely many odds. So it is in these unions because there's going to be even numbers in these indices. So x will belong to this union, but it won't belong to this intersection because there's going to be odd indices in that intersection, and x won't be in some of those. So x belongs to all of the unions and therefore the intersection of all the unions, but it doesn't belong to any of the intersections, and therefore it doesn't belong to the union of the intersections. It is in the limsup, but not in the liminf, and this was for x's in between 1 and 3. Okay, another example. The liminf is always contained in the limsup. So once again, we have this notion that liminfs are smaller than limsups, but we're not talking about inequalities of numbers. We mean in terms of set containment. The set, the liminf, is smaller than the set, the limsup. So suppose you are in the liminf. This is just a set containment proof, so I just need to show if I'm in the left set, I must be in the right set. If I'm in the liminf, there is a capital N past which x belongs to every a sub n. But therefore, it's in any single one of these unions because past this index, it's in all of them. Okay, so it's definitely in that union. Therefore, it belongs to the intersection of all these unions because it's in every single one of them. So it is in the limsup. If you only fail to be in the sets finitely many times, remember that's the liminf, you only missed finitely many times, well then you definitely were in there infinitely many times. Past a certain point, you are in every single an, so you're definitely in infinitely many of them. If you're in the limsup, if you're in the liminf, then you're in the limsup. The liminf is a smaller set, it has more restrictions on it. It is in some sense more difficult to be in the liminf than the limsup. Well, now we're going to apply basically a familiar definition. We've established the liminf and the limsup both exist. They're just set constructions, they definitely exist. And also the liminf is a subset of the limsup. Well, if they're equal, then you call it the limit. Okay, same idea. If the liminf equals the limsup, that's what we call the limit. So try to work some problems. Okay, notice in number 1 and number 2, these are not intervals. These are sets of very specific numbers. Try to show that they have the given limits or liminfs and limsups. Number 3 and number 4 are about constructing examples with certain properties. So hopefully you've been finding these videos helpful. Go ahead, like, subscribe, comment, I don't know, send YouTube a handwritten letter, whatever helps. Moving on. Just want to remind you that limits of sets and limits of sequences are different ideas. They're computed differently, they're defined differently, they don't necessarily mean the same thing. Okay, here's an example. AN is just the set n. So the set containing 0, then the set containing 1, then the set containing 2, and so forth. And Bn is just 1 over n. In both cases as sets, the limit is the empty set. But if I wasn't looking at them as sets, but as numbers, the limit of n is plus infinity, and the limit of 1 over n is 0 as a sequence of numbers. You just get different things because you're thinking about them in different ways. Okay, so don't mix these two notions up. And I'll be honest, limits and limits and limsups of sequences of sets really aren't going to come up. The purpose of this section is just to point out you can define it. And while it won't come up in this course, it is something people talk about and could care about. So mathematicians like to take definitions that exist in one context and just sort of see, hey, what happens if I start applying this in other places? Can we prove similar results? Do we get entirely new behavior? So don't be afraid to experiment, taking ideas that we develop for one reason and asking, could it be used for something else? Well, that's going to wrap up our work in Unit 2, Structure of the Real Numbers. After this, we're going to move on to really working with sequences in Unit 3.